All right. Thank you very much, Ellen, for that nice introduction. Good day, everyone. I'm very excited to talk about some of my PhD research about ozone depletion events at Villum Research Station. But first, I would like to thank several people here. This was a very long process. This work actually started in the pandemic, and it was only recently last year that it was published in Atmospheric Chemistry and Physics. I'd like to thank my co-authors, Jens, Henrik, and Lisa Lotta for all of their help, the wonderful technicians, Bjarne, Kjell, and Crystal, for all of their help gathering the data and the measurements over the years, the Station North staff, where Villum Research Station is located, as well as the Royal Danish Air Force for providing logistical support. And I would be remiss if I didn't mention my past supervisor, Julia Schmala at EPFL, and my current supervisor, Branka Miljevic at QUT, for supporting me while I continue to work on this project. And I'd like to thank all of the funding agencies that funded me in my PhD, as the Villum Foundation, iGOSP, iClimate, as well as iCube. I'd like to begin with some introduction and motivations. I chose this picture because every time I see Aurora Borealis, I feel very motivated to do science. So for context, here we have the ozone seasonal cycle at Villum. During the winter, we have high and stable values due to transport from the mid-latitudes, as well as diminished sinks in the polar night. During the summer, we have low, but also somewhat stable values. This is due to little sources of ozone with the low absolute humidity and low NOx values, and then increased photochemical destruction. Although interestingly, in the spring, we see low but highly variable values of ozone, sometimes even reaching 0 ppb. And these are these ozone depletion events. To give you some more context, here we see a couple of days of ozone mixing ratios. And in this study, we define an ODE as being less than 10 parts per billion. So these ODEs can be quite complex, with some quickly dropping to very low values only for a couple hours to quickly rebound. Whereas the next day, we have a slower decrease and then near 0 values for over a course of a day with a slow rebound up to previous levels, only to quickly drop down again for several hours. And then the rebound was interrupted again to give us low values. And this just goes to show the complex behavior of these ODEs. So ODEs are closely tied to halogen chemistry, and so I quickly want to walk you through some of the chemical mechanisms leading to ODEs and these halogen explosion events. We start with molecular halogens, either bromine, chloride, or iodine, or a combination, which then photolyze to give you these atomic halogens, which then react with ozone to give you a halogen monoxide. Now, this halogen monoxide can quickly photolyze and react with oxygen to produce ozone again, resulting in a null cycle, or it can undergo self or cross reactions to reproduce this molecular halogens. But it can also undergo reactions in the atmosphere with the hydroperoxy radical as well as nitrogen dioxide. And these products will quickly deposit onto surfaces. And there they undergo multi-phase reactions with saline and acidic compounds to reproduce these molecular halogens. So we can see why they're called halogen explosion events, as one halogen atom can go on to produce two. This is an autocatalytic reaction which quickly proceeds, destroying ozone and can produce high amounts of halogen species in the atmosphere. So one thing that is needed for these halogen explosion events and ODEs is a frozen haline and acidic surface, such as snowpack, either on terrestrial or marine environments, sea salt, aerosol, refreezing leads, or brine migration, amongst others. So here we can see a schematic of the chemical mechanisms which I just showed. Briefly, we have the emission, photolysis, whereas it can go on to react with ozone or VOCs, but also can undergo these cross reactions as well as atmospheric reactions that will produce the deposition, and this cycle can start all over again. One important aspect is that this process can also occur on aerosol particles in the atmosphere. Studies have demonstrated this to prolong these ODEs, thus allowing them to be transported over great distances in the Arctic. Another important aspect is once temperatures reach melting point, halogen production largely decreases and ceases. While we still have the deposition of these halogen species, its re-emission is largely ceased by the surface not being frozen anymore. So now that we've seen how these halogen explosion and ODEs occur, we want to see why are they important. Ozone, being a greenhouse gas, absorbs in the shortwave and longwave spectrums, and thus affecting the radiative balance. As we just saw, ozone is a key ingredient in these halogen explosion events. And both of these processes can go on to affect the atmospheric oxidative capacity, which has implications for VOC oxidation, as well as secondary organic aerosol formation, especially considering dimethyl sulfide, but also importantly for human health, halogen explosion events as well as ODEs are closely connected to mercury oxidation and deposition. And then recent study has shown that ozone depleted air masses from these ODEs can be exported to the mid-latitudes and thus affecting the radiative balance outside of the Arctic as well. A more pressing motivation is the changing Arctic environment. The Arctic is undergoing increased temperatures, as we can see here, at a rate much higher than the global average. And this is causing sea ice to decline at a rapid rate. But not only is the total volume of sea ice decreasing, as we can see, multi-year ice is being replaced with first-year ice. And then this decline of sea ice is likely influencing changes in the cloud cover. Thus, there is an urgent need to resolve some of these current unknown ODE processes to understand future implications. Therefore, this study addresses these following research questions. What are the temporal characteristics of ODEs and how have they changed in past decades? Where are the source regions for these ODEs and how are different surface types affecting them? And then finally, what are the environmental drivers of these ODEs? First, I would like to describe some of my methods quickly. We can see in this picture some of the harsh realities of doing Arctic field work. This picture was taken after a snowstorm at Villum. We can see bent antennas, bent sonic anemometers, and disturbed mercury instruments. And as we'll see, the full damage to them at the end of this presentation. So ozone was measured at Villum Research Station, located at the Danish military base Station Nord on northeast Greenland from the mid-90s to 2019. We can see here this nice researcher's house, the air observatory where ozone was measured, along with Pfluger's Hut, another building located in close proximity. And then Villum is ideally located to study ODEs, being perennially surrounded by sea ice, but also being in close proximity to multi-year ice as well as first-year ice, and located on the Greenlandic continent. So as we said before, ODEs are defined as ozone mixing ratios below 10 ppb. And we just did a binary classification where if it was below this, it's classified as an ODE, and above it as a non-ODE. Then to explain and interrogate the drivers of these ODEs, we use meteorological data measured from Villum and from the Danish Meteorological Institute. We also did air mass back trajectory analysis with the high split model using 1 week trajectories starting from 50 meters using the INCEP NCAR meteorological data and surface types from the National Snow and Ice Data Center. So for each step along the trajectory, we analyzed if its altitude was below the mixed layer as produced by high split. If it was not, it was classified as being above the mixed layer. If it was, we classified it into one of these four categories: land without snow, the open ocean or the sea, sea ice, and snow. It's important to note here that if a trajectory step was classified as sea ice, the data set we used cannot distinguish if there is snow or not on top of the sea ice. So we stuck to the original labeling and classified it as sea ice, although it is very likely that a lot of the sea ice contains snow on top of it. And then we integrated these different surface types over the entire trajectory length to get a percentage of time the air mass experienced exposure to these different surfaces or was above the mixed layer. To understand some of the environmental drivers of ODEs, we use this in situ meteorological data along with these air mass history variables and put them into a supervised binary classification machine learning model to predict the occurrence of ODEs or non-ODEs. We tested several models, ultimately setting on the extreme gradient boost model for several reasons, mainly because it was quite accurate, correctly identifying 87% of these ODEs. Most importantly, it's able to handle data that is collinear, and that's very important for meteorological data, which oftentimes is covariates. And then finally, it was computationally inexpensive, the entire pipeline running on my laptop within a matter of minutes. One of the drawbacks of this XGBoost model is there are several complex hyperparameters that require tuning. Hyperparameters are just different configurations of the model which can affect its performance. Here we used a Bayesian optimization method to ensure that we have the optimal hyperparameters tuned, thus ensuring the proper performance of this model. Bayesian optimization also allows for this to happen within a reasonable time frame. And then another drawback of this XGBoost model is its black box nature, meaning that for a human, it's difficult to understand the exact workings and every single decision made by the model. Therefore, we use the Shapley additive explanation, or SHAP values, to interrogate our model. While I don't have time to go into the exact workings of this SHAP, the most important thing you need to know is that positive SHAP values mean the model is more likely to give an ODE prediction for that variable. And then a negative SHAP value for certain variables means the model is more likely to give a non-ODE prediction. So this brings us to our first research question. What are the temporal characteristics of ODEs and how have they changed? I took this picture after this snowstorm, which I mentioned earlier. While walking to the cantina, we noticed that the Danish flag was flying, which was quite strange because there was hardly any wind this day. And then when we got closer, we saw that this flag was frozen in place and it was not flying. So here we can see the ODE frequency for each month. And I've tried to keep a consistent color scheme throughout this work, with March being depicted in red, April in black, and May in blue. We can see a consistent increase from March to May. And then we analyze the ODE duration, or how long a single ODE lasts. This also increases from March to May, although the medians are quite similar for each month, and these notches on these box plots overlap, indicating that these medians are not significantly different on a 95% confidence interval. This is one interesting result, as we would have guessed these ODEs would have lasted longer and longer as we progress in the season. So then our next question was, how have these changed over the course of this measurement period. So to analyze this, we did a trend analysis on both of these parameters for each month. As you'll see in a bit, we analyzed the significance of these trends, with the black bars being non-significant, red bars having a higher p-value, thus lower confidence in these trends, and then blue bars having a very low p-value, thus we are quite confident. And then these thin red error bars represent the confidence interval. So here we can see the trends for the ODE frequency, which is increasing in May, although this is with quite low confidence. And then the ODE duration is significantly increasing in April. We also analyzed the start, end, and duration of these ODEs for each spring season and for each month separately, although they showed no significant trends. While normally we're not very interested in trends that have low confidence, when you combine this with trends of ODEs from other Arctic stations located within proximity to Villum, we can see there is a significant increase in the frequency of ODEs, especially when we consider the record from the mid-90s when this study started. Although interestingly, a recent paper showed ODEs are actually decreasing in northern Alaska at a Ukavik or Barrow site from the 2000s to the early 2020s. We see a decrease here, which is quite interesting. These two Arctic stations, or several Arctic stations located on either side of the Arctic show opposing trends. When we analyze the annual trends of ozone at several Arctic stations from Kathy Law's recent paper, we can see Alert, Villum, and Zeppelin are all experiencing increasing trends in ozone mixing ratios annually, while Ukavik/Barrow is not experiencing a significant annual increase. When we analyzed the monthly trends at these three stations, we see this is mostly driven by trends in the wintertime. This is opposed to the trends we see for Ukavik, which are mainly in the spring or in summer. So some of the take-home messages from the temporal characteristics, we see an increase in the frequency and duration going from March to May, and that this is increasing at Villum for the frequency in May and the duration in April. And coupled this with trends in the frequency from the Canadian archipelago show a consistent increase, while as a site in northern Alaska shows a decrease, showing these trends in ozone mixing ratios and OZEs are not homogeneously geographically distributed around the Arctic. And then finally, we see these ozone mixing ratios are increasing, although at different times of the year. This brings us to our next research question. What are the ODE source regions and how do different surface types affect them? So to analyze the different source regions, we constructed a trajectory frequency map consisting of 2x4 concentric latitude-longitude grid centered on Villum. We then counted the number of trajectory points within the mixed layer in a grid cell, normalize this by the total number of trajectory points within the mixed layer in all grid cells. And this was repeated for ODE and non-ODE trajectories for each month separately. We then subtracted the non-ODE frequency from the ODE frequency, and this difference gives us the referential source regions for ODEs. And we repeated this for trajectory points classified as snow and sea ice as well. So here we can see the results of this analysis with ODE frequencies in the top row, non-ODE trajectory frequencies in the middle row, and then the difference in the bottom row. So focusing on March 1st, we can see the source regions include the Canadian archipelago as well as the Chukchi Sea. During April, it is mostly over the Central Arctic Ocean, And during May, it's mostly confined closer to Villum within the Central Arctic Ocean. It's quite interesting to note that as we progress from March to May, these source regions get closer and closer to Villum. When we analyze the trajectory difference for trajectory steps over snow, we can see the snow in the Canadian archipelago is consistently a source region. And then in April, some of the coast around Alaska and Siberia make a small contribution. And then during May, the Greenlandic continent is also a source region for trajectory steps over snow. And this is supported by studies that show bromine monoxide hotspots are located within the Canadian archipelago as well as the coast during March and April. For trajectory steps over sea ice, we see the source regions largely mimic the trajectory source regions I previously showed, the Chukchi Sea, the Central Arctic Ocean, and the Central Arctic Ocean located closer to Villum. When we do a qualitative comparison to the average sea ice age seen here for the spring months, we can hypothesize that during March, first-year ice in the Chukchi Sea is making a contribution here, while in April and May, it is a combination of multi-year and first-year ice. So here are some of these take-home messages. The Central Arctic Ocean is a source region for ODEs, as well as air mass exposure to sea ice, as well as snow on top of the sea ice. For the snowpack, the Canadian archipelago and Greenlandic continent make a contribution. And then finally, as spring progresses, these source regions get closer to Villum, with first-year sea ice making a contribution in March and a mix of the two in April and May. So this brings us to our last research question. What are the environmental drivers of these ODEs? Again, to discern this, we employed our machine learning model, and I want to show you mainly the results of the SHAP analysis. This is the most interesting and can give us the most information. Just as a refresher, positive SHAP values means a variable is more likely to make a contribution towards an ODE prediction, whereas negative SHAP values means that variable is less likely to give an ODE prediction and more likely to give a non-ODE prediction. These SHAP values can give you two different approaches: a global SHAP explanations, which can tell you which variables are most important overall in your model. To do this, we calculate the mean absolute SHAP value for each variable and compare their magnitude. For example, we can discern, is radiation or temperature more important overall for predicting ODEs? While this gives us important information, it does not tell you how these variables contribute in a positive or negative way. And so therefore, we employ a local SHAP explanations where we look at each observation. And this can tell you how these different variables affect your model prediction. To do this, we bend each variable into 15 equidistant bins and calculate the mean SHAP value for each bin, as you'll see on the next slide. And this can tell us how different values of temperature, for example, affect the prediction of ODEs. So here we see the global SHAP explanation, again, is absolute value of mean values. So when we analyze March through May, we can see here the most important variables being sea ice, exposure to sea ice, radiation, temperature, and pressure, with the other variables making a minor contribution and a drop-off after these. This gives a lot of physical sense, indicating our model is able to produce physically meaningful results. Interestingly, when we analyze this on a monthly basis, we can see these variables change. Not these four variables, but their order changes. For instance, in March, radiation is the most important variable. And this is, again, makes physical sense, as radiation is oftentimes limited in March and polar twilight. In April, we're well into polar day, and therefore sea ice makes the most important contribution to our model, air mass exposure to sea ice. And then moving into May, where we have warmer temperatures, we can see temperature makes the most important contribution to our model prediction for ODEs. Next, we wanted to analyze how these variables, each one affects our model prediction. So again, to do this, we bend each variable into 15 equidistant bends. And the lines here represent the median SHAP value for each bend as depicted on the left axis. And then we have a histogram, again, split by each month, with March in red, April in this black, and May in blue. And this is indexed on the right axis here. So for instance, we can see low values of relative humidity, very dry conditions. Our model predicts this will more likely be a non-ODE because these negative values means it's less likely to be a positive prediction or an ODE here. While for average values and above average values, relative humidity makes a very small contribution and hovers around 0, meaning it's not very important in our model. So we interpreted this as very dry air masses subsiding from aloft, bringing in ozone-rich air masses, and therefore less likely to be considered an ODE. The next variable was wind speed, and interestingly, at Villum, there's oftentimes very low wind speeds, and around the average wind speed does not make much of a contribution. And as we get to higher and higher wind speeds, it's mostly negative, but also a very low value. And only in May does high wind speeds actually make a contribution towards a model prediction of ODEs. This was quite interesting, as sites such as Zeppelin and Alert and Resolute have also showed that cyclones can induce blowing snow, which are a source of halogens and thus causing ODEs. Although at Villum, they're not oftentimes not very high wind speeds, and so therefore it does not make such a very large contribution. Moving on to temperature, this was by far one of the most interesting results of our analysis. So several studies have shown ODEs and halogen explosions to be temperature dependent, while as others have shown them to not be temperature dependent. And our analysis here shows that up until a certain point, temperature has very little effect on our model prediction for ODEs. Up to around -12 degrees, only does temperature start to affect it negatively. So temperatures higher than 12 degrees, approaching 0, you're less likely to see an ODE. Moving on to radiation. It also displays a threshold value where higher values of radiation are almost linearly correlating to a positive prediction of ODEs, where lower values are more likely to give you non-ODEs. Again, showing very much physically consistent results. For pressure, we see that lower values of pressure are less likely to produce an ODE. Low values of pressure are also associated with cyclones, although these don't happen very often at Villum. And above average values of pressure either produce a small result or a positive result for ODEs. And then higher amounts of pressure are associated with clear, calm days, again, with some stagnation, thus confining all of these reactants to a very low boundary layer. For wind direction, this was quite clear. Northerly wind directions give a higher probability of producing ODEs. This makes a lot of sense as the sea ice is directly north of Villum. Speaking of sea ice, again, it produces a threshold value where values above this are linearly correlated positively to a prediction of ODEs. And then lower values are less likely to give you an ODE. What's also interesting is this threshold value is around 17%, indicating air masses don't need to spend a great deal of their entire trajectory over this week to produce a positive prediction for ODEs. Moving on to another cryospheric surface type, snow, was a little bit perplexing. Air masses don't usually experience contact with the snow, indicated by the most frequent values being quite low. And we were quite perplexed why the next bin produces such a negative SHAP value. And we're still investigating this. But again, we see after a certain amount of exposure to snow, only does it then give a positive prediction for ODEs. And then lastly, we have air mass time spent above the mixed layer. This was also quite perplexing, as a lot of this work and previous work has shown ODEs to be a surface-related process. Although, as I showed, this can occur aloft on aerosol particles. So after about 50% of the time air masses are above the mixed layer, they produce a positive contribution to our model output of ODEs, although this is quite small. And below this, it produces a much larger negative contribution. So we were quite perplexed by this result, and we wanted to investigate this a little bit further. So what we did is we analyzed the distribution of our input variables for a correctly predicted ODE, as you'll see in blue, or an incorrectly predicted one in red for the entire spring period. So here we can see these two variables, which are interconnected, as if it's below the mixed layer, it can be over sea ice or snow. And then this variable being the one in question, which we wanted to interrogate further. So as we can see for the violin plot in blue here, the median of this is depicted in the thick black line. So for a correctly predicted ODE in our model, we have much lower values than when we are incorrectly predicting an ODE, and vice versa for correctly predicted ODEs for sea ice are much higher than incorrect ones. And this gives credence to our model that it is actually learning these relationships and is not an artifact within our model. This led us to consider other factors such as the input variables produced from high split themselves. So this could be, we were calculating two long trajectories. We did calculate 1 week, and this was based on the longest ODE observed at Villum to be 1 week, and therefore we wanted to capture all possible source regions for all of these ODEs. And the more time you further backward in trajectory, the more time you are spent above the mixed layer. So this could be contributing to it, as well as a misrepresentation of the mixed layer height. Within high split, it could be too low. Reanalysis data is notoriously is hindered within the Arctic due to a lack of observations, as well as difficulties in satellites due to the high contrast with the sea ice. High split also has inherent uncertainties within itself, increasing proportionally with the trajectory length. We chose a starting altitude of 50 meters, as the boundary layer height of Villum was shown to be around 100 meters in the spring. Therefore, you wanted something in the middle of this. Although this could be too high. If we start it too high, then more of the air mass will spend above this mixed layer. And this shows just the need for a careful consideration of air mass history, although this can be quite challenging for multi-decadal data sets. We only discovered this at the end of our analysis, and therefore redoing 20 years of trajectories was unfeasible at that point. So just to reiterate some of the take-home messages for the environmental drivers of ODEs. These mainly occur under clear, calm conditions, high amounts of solar radiation, cold temperatures, high pressure, low wind speeds, stable boundary layer height that allows this accumulation of halogen species, as well as hinders the mixing of ozone-rich air above. And then northerly air masses indicated by the northerly wind direction. Higher RHs are interpreted as coming from over the sea ice, where cold temperatures and water vapor evasion will produce a higher RH. Conversely, lower RHs are indicative of subsiding ozone-rich dry air masses. And then coming from a northerly direction oftentimes corresponds with high exposure to sea ice. The most important variables for ODEs were physically realistic, although they changed. Interestingly, they changed as the spring progresses. March is oftentimes limited by solar radiation, thus making it the most important variable. During April, there is sufficient radiation and sufficiently cold temperatures, and thus emphasizing the need for exposure to sea ice, thus producing some of these halogen species. And then in May, we have temperatures closer to freezing, thus limiting these colder temperatures, making temperature the most important in May. And then interestingly, certain variables displayed threshold values for the positive prediction of ODEs. And then lastly, it's quite important to carefully consider how you're constructing these air mass history trajectories as well as these variables. Now I'd like to discuss some of the effects of climate change on ODEs. Hopefully this will spur some interesting discussion afterwards. So as we saw in the beginning, the Arctic is experiencing warmer temperatures, and temperatures above freezing will cease halogen production. And then as we showed in this study, temperatures above -12 will act to limit the probability of ODEs, and this will likely have the largest impact in May when temperatures are closer to both of these two values. We also saw the Arctic is changing in its cryosphere. There's less sea ice, less snow on sea ice as well as on the land. The snowpack is also getting shallower on sea ice and thus being more salty. First-year ice is replacing multi-year ice. And although first-year ice is saltier than multi-year, both have been shown through observational studies to be sources of halogens. And then there's an increased occurrence of open leads. Open leads, through their refreezing, can increase halogen production, but also open leads can induce convective mixing, bringing down ozone-rich air, thus ceasing these ODEs. And then there's increased cloud cover, likely owing from less sea ice, and this can limit the amount of surface radiation reaching the surface. And then studies have shown changing transport patterns at Villum as well as Zeppelin to more southerly regions, which could affect the exposure to sea ice. And then finally, I'd like to highlight some future directions. I realize I'm about out of time here, so quite quickly, we've shown that ODEs or an ozone is changing within the Arctic, and we need to a detailed investigation of these underlying causes, likely through modeling studies. Direct halogen measurements could tell us the relative contribution of each one, as well as their oxides, although deploying complex mass specs long-term in the Arctic is a logistical challenge. Determining the causes and what's driving the duration and termination will help explain how ODEs will respond in the future. We need to carefully consider air mass history, incorporating time-resolved variables as well as a quantitative exposure to these different cryospheric surfaces. Vertical measurements of ODEs can help with the radiative forcing estimates, such as the upcoming Terra Polar Station mission. This provides an opportunity to deploy vertical measurements through helikites on the sea ice. Finally, we could apply this same methodology to different Arctic stations to understand some of these geographical differences. And we need to improve model parameterization of halogen emissions, which are notoriously poor at reproducing these ODEs. Finally, thank you all for your attention, everyone who joined here today, everyone who's helped me along the way. And I'm very happy to discuss this work.
Thank you so much, Jakob, for this excellent talk. So we're now going to open the floor for questions and discussion. I'd like to encourage everyone to participate, so feel free to raise your hand, turn on your video if you're comfortable doing this. I mean, it's always nice to see some faces. Or you can also type your question in the chat and I'll be happy to read it out loud. So let's try to keep this as interactive and informal as possible. So who would like to get us started? I know you had a question in the chat. Perhaps you want to, yeah, perfect. You're here. Go ahead.
Thanks, Helen. Hi, Jakob. Very nice talk. And I was very happy to read the paper also. It was a really nice analysis that you've done on a really long data set, which gives us a lot of insights, as you've shown. Uh, I have lots of questions about this, but the first one was about this lower sea ice threshold. So it's at 17%, it's a pretty low threshold of sea ice to have for an ODE, which indicates that yes, sea ice is important, but do you think that's also indicative of non-sea ice sources of halogens also playing a bit of a role? And if so, would it be something else besides bromine, like iodine, for example, which can come out from the ocean surface itself? Do you think that's indicative of that playing a role?
Absolutely. This was my first thought as well. Halogens can have biotic sources from the open ocean. Thus, they could also be contributing, as well as possibly aerosol particles and these reactions within them due to our setup in our air mass history variables. It is either being below or above the mixed layer, and thus, if it's below the mixed layer, it's one of these different surface types. So yeah, absolutely, it could very well be other things than bromine, especially in the summertime, as some of your work has recently shown. And then, thank you very much for those very nice comments. It means a lot.
I have a few more questions, but I'll
Absolutely.
let others ask some before I get back.
No one else raised a hand, so go ahead.
Okay. The other thing was, have you looked at the bromine plots, so the satellite measurements of bromine to see if that kind of correlates with some of the inferences that you have drawn?
This is one thing that I really wanted to do, but it did not ever materialize within this study. Um, a this took a very long time to produce from the first plots I produced to publication. And it really taught me the limits of any research study as well. There, there was not enough time. There's a lot of nights and weekends working on this as I've finished my PhD and completed one postdoc and started another from the time this was started to was finished. So this is definitely a future recommendation, incorporating satellite measurements of BRO into our air mass history variables, especially the time-resolved air mass history. This could very much help pinpoint some of these processes contributing ODEs.
Yeah, yeah, and that would be very interesting to see because it would also give you some insights as to is bromine the main driver or other
Mhm.
things also contributing to it, right? And whether satellites
Absolutely.
are picking up all the ODAs in terms of bromine or not. That would also be a good check. And the last question before somebody else asks is uh, you used a threshold for ozone to define an ODE, like a 10 ppb flat threshold. Um, and do you think there is a bias introduced by that towards your northern air masses? Because I'm assuming if your air masses are not coming from your north, they're going to have an inherently higher amount of ozone in it.
Mm.
And hence, even if there's a depletion happening, it does not cross the 10 ppb level. So do you think that causes a bias or you're not worried about it because it won't really change the oxidizing capacity by a huge amount?
This is a very good question. And Jens and I worked very hard on how we actually define this. At first, we wanted to follow the methodology of Halfacre et al., where they employed more of an algorithm to show when ODE starts dropping below a seasonal threshold, and then as well as increasing above these minimal values during ODEs. This proved quite complex and produced some artifacts. And then we tested different thresholds. I believe we chose 15, 10, 5. All of those showed quite similar results and were more straightforward. A lot of other studies have also used 10 ppb as a threshold value. We wanted to be consistent with them for comparison to the previous literature. And then I recently saw a paper in ACPD that compared these different threshold values of 10, 5, 4, as well as a variability threshold, and using an isolation forest, which is another machine learning algorithm, to try to classify these different criteria for ODEs. They actually showed the threshold value of 10 ppb was arguably the best. And I showed some of their work in the presentation about the trends from Ukavik. So you're absolutely right that the air mass origin would make a difference whether or not these values or these labels of ODEs are being influenced. I thinking about it, I'm not too concerned about that, since most of our ODEs are coming from the Arctic. We can see the central Arctic Ocean. But you really need the right mix of conditions. You do need contact with a frozen heterogeneous surface that's saline and acidic to produce these halogen explosion events. You need sunlight. So that's not to say this couldn't occur when air masses are coming from the continent or from the coast. Just the right mix of this occurs when it's mainly over the central Arctic Ocean.
Yeah, I completely agree with that. But I wonder whether we should qualify saying ODE events are not representative of ozone depletion potential, right? That those things might be decoupled depending on the air mass origins.
This is a good point. Yeah, absolutely. We wanted a simple classification, especially for our machine learning model. A simple binary 1 or 0 very much sufficed and proved effective. But you've also make a good point, classifying the strength of these ODEs, how long they last. This was another avenue that we wanted to explore, but it didn't quite fit in with the scope, and the paper was quite long. And so we definitely had to limit some of what we wanted to include, and depending on the time constraints as well. Other future directions could very well be analyzing how deep these ODEs actually occur, not just dropping below 10. As we saw in the beginning, sometimes it can get 7, 8, and that's also classified as an ODE, whether or not it's completely depleted or not. So this could very well be an avenue for future research.
Great. I look forward to the next paper then.
Thank you very much.
Thanks, Anna, for these questions. Bronca, go ahead.
Did I unmute myself? Yes.
Yeah.
Okay. Yeah. Okay. So I think my question, I'll start with the question, are going to be a little bit more general, because my research doesn't have much to do with ozone. But okay. So if I remember correctly, you showed that the long-term trend for Villum shows that ODEs are kind of increasing, right?
Mm-hmm.
Okay. And then we need frozen acidic surface for halogen explosions. But then on the other hand, sea ice is decreasing and ODEs are increasing. So how does that fit in the whole story? Or am I missing something? So we kind of have less ice, but more ODEs.
No, you're absolutely right. This is a bit contradictory, and I would feel the best explanation would be while sea ice total extent is decreasing, first year ice is becoming more prevalent. And first year ice is saltier, and therefore more of these salts are ejected during the sea ice formation, and therefore they have more halogen production potential within its surface. We've seen that bromine monoxide has increased over the entire Arctic within the past 20 years. This would directly contribute more halogen species.
So
Possibly,
satellite data is showing that.
yes,
this.
satellite data has shown this. It could very well be also changing transport patterns, even though some previous work has shown it's more likely to be southerly air masses, not northerly air masses in the spring at Villum, also the close station to on Zeppelin, on Svalbard. And so there's several different factors that could contribute to this. And this is definitely a future avenue for research. Especially when you consider across the Arctic, in northern Alaska to Ukavik, we see an opposite trend. ODEs are decreasing. That could be, increased anthropogenic influence. There are many oil fields on Alaska. A lot of Carrie Pratt's work has shown, and these oil field emissions can directly influence ozone. I feel like I'm missing another reason for.
Anoop has put in the chat iodine.
Iodine, yes. Thank you.
And my second question would be, I have to turn the story to my side, your now also side of the globe, and just ask you to kind of compare the Antarctic ODEs versus Arctic. So I believe that there's more in Arctic, but do you know anything about Antarctic ODEs? And in terms of frequency, let's say, that's easy.
To be honest, I'm not the most up to date on the literature of Antarctic ODs. I also hesitate to say that they're more frequent. I'm really comparing the two. The Arctic is an ocean surrounded by land, and then the Antarctic is a continent surrounded by an ocean. To be honest, I hesitate to really give an answer. And as you know,
this is just out of curiosity. I know.
Ozone anymore. But definitely the halogens. There's been differences shown in the amount of halogens between the two poles. So this would definitely directly affect ODEs. I would very much be interested in how these halogens are affecting DMS oxidation, which is much more prevalent to my current work.
Can I just add on to that?
Absolutely, Anoop. Please, thank you.
Yeah, so it's a very good question about the differences between the poles. There's no doubt that there's enough halogen activity happening in Antarctica, but there is a huge difference according to where in Antarctica you are. So, for example, if you're in the Weddell Sea, roughly the halogen activity is a lot more active as compared to the Eastern Antarctic. So you get similar levels to the Arctic of bromine, etc., in the Weddell Sea. But on the Eastern Antarctic side, you get much, much lower levels. And not just bromine, but even iodine is extremely active within the Weddell Sea, which can be seen by satellites, which is probably the only place in the world where you can actually see satellite, columns of iodine oxide. So that's completely absent in the East Antarctic also. And it's been, yeah.
Oh, so sorry, I didn't let you finish. I'm sorry.
No,
I was
please
just,
go ahead.
really curious about the satellite data for iodine oxide. So there's nothing, or nothing observable in East Antarctica, right?
No, it's pretty much. I mean, close to the Davis Sea, there's a little part where you can see some, but yeah, it's definitely not as prevalent as in the West Antarctic, for sure. But bromine, it's all over. So wherever the sea ice, seems to show. So it's like a ring around Antarctica where you see lots of bromine activity. But the iodine, there is a huge difference according to the location itself.
Yeah, I
Well,
wanted.
that kind of,
Go ahead.
sorry.
Sorry.
I just wanted to say that for iodine and related to that iodic acid, that kind of fits into our field observations that are kind of mainly in East Antarctica, kind of below Australia. And we didn't measure any bromine related species, but only, like iodic acid, and that is disappointingly low.
Yeah. Iodic acid seems to show up everywhere. I mean, even if you go to
Yeah,
space, I
we
think you'll
see
find
it.
it now.
We see it. We see it all the time, but like
Low levels, right? Yeah,
yeah.
Yeah, I just want to say, so following up on what Anouk just said about depends on where you are in Antarctica. Back then we had data from Dumont d'Urville, so eastern side, south of Australia. So we're measuring mercury and ozone as well, and we had a few depletion events, but just, out of 10 years, perhaps one or two. So it's very rare,
Okay.
despite it being a coastal station. So the chemistry is completely different, and we're mostly influenced by katabatic winds flowing from the
I
plateau.
know.
And so
Yeah.
NOx levels and the chemistry is very different. So I guess that's why as well. And I had a quick question for you, Jakob. So you said the maximum the frequency is higher in May and then April and then March. And I remember reading a paper where at Alert, initially they saw the same thing, and then there was a shift where now the maximum is in April. And I was wondering if you could comment on that. Why would it be different? I mean, the two stations are not that far away.
I think I know this paper too, about mercury depletion
Yeah.
events. And if memory serves me correct, it might have been the other way, that it was earlier in April, and then later in the record it was more in May.
No, I think it's coming.
Like Stefan Cole and Stefan, I believe is the paper.
Yeah, I'll check
But I
that.
could also be wrong. There's several different things might be contributing to this. As we, the length and what time period you analyze could also make a big difference. Longer time series, you can either detect more non-stationary data, more positive or negative trends. But then why would a seasonal shift be occurring is a really good question, and not just an increase or a decrease in 1 month or the other. It could be a number of different things: changing transport patterns, changing chemistry, increase in the cyclonic activity or wind speeds, more blowing snow, changing cryosphere, with more or less first year, multi-year ice or open leads. And then the snowpack on top of all of this as well. A shallower snowpack will be saltier and have a higher halogen production potential. Teleconnections could also be making a big difference for here. So definitely a question that requires
for
more
that
research.
investigation. I think everyone's leaving. I think it's time to go.
Yeah, it is
Over. Thank you so much, Jakob. It was super interesting.
Thank you, Ellen,
Yeah.
for hosting. All right. Give my best to Elon, yeah?
I will.
All right.
Bye
Thanks,
bye.
everyone. Have a
Bye-bye.
nice day.
Bye.